start the recording. Okay, I'm going to do this again. So how many? Okay, so we're recording here. How many hydrostatic force? Okay, this deals with hydro's water. So force acting on an area. How many notice that when they dive into the pool, as they go deeper down, they're feeling more force on their body? All right, so you're going to have Sean and let's see, Michelle and Jacob and all right, quite a few of you, Samuel and you know, there's a principle of fluid pressure, an important principle the book mentions. It's the experimentally verified fact that at any point in a liquid, the pressure is the same in all directions. So, for instance, a diver feels the same pressure on nose and both ears. Okay, so the pressure acts on your body equally. Okay, all right. Let me give you a moment to copy this example down, and we're going to go right into solving this example. All right. So let me give you a moment to copy the example down. Now, this example, there is an example in the book, but these two examples I'm doing are more like going to help you with the homework. So and it gives you a variety of a wider variety of examples. So, okay. Okay, so in this problem, we have an aquarium. Okay, we have an aquarium that's 5 feet long, 2 feet wide, and 3 feet deep. That's kind of a standard size, I believe, for an aquarium. And it's full of water. Okay, now there's water pressure on the bottom of the aquarium. Okay, and then there's force on the bottom of the aquarium, right? The bottom of the aquarium, if it's made of glass, it has to be strong enough to withstand the force. And also the ends of the aquarium, okay, have to be able to withstand what's called the hydrostatic force. So what might be an important thing regarding water that we need to use here? If we're going to, let's do part A first. Find the hydrostatic pressure on the bottom of the aquarium. So what might be needed? Do you think the density of water is going to be important? Sean? Sean thinks so? Absolutely. Okay. And another thing that's important, notice they're saying the bottom of the aquarium. The bottom of the aquarium. So we're going to find this hydrostatic pressure. Let me show you how to do this. May I go to the next page? Does everyone? Okay, Jacob has it copied okay. And Nicole. Jazzy, and wonderful. Sean, okay. So I want to mention that the hydrostatic pressure, what do you think the unit should be if we're talking about pressure on the bottom of the aquarium? Okay. Okay. So I'll give you a hint. I'll give you a hint. Okay. So the bottom, the top part is going to be pounds. Okay, pounds. That's going to be, so for hydrostatic pressure, the top unit is when we get our answer, whatever it is, the top unit is going to be in pounds, but it's pounds per what? What do you think should be in the denominator here for the hydrostatic pressure?
Area.
What unit? I'm sorry?
Square feet.
I heard, did somebody say area?
Square feet.
That's right. Nathan and Leping are saying the same thing. That's right. Square feet. Because we're talking the bottom of the aquarium. The bottom of the aquarium is a surface, and a surface has area. So hydrostatic pressure, it makes sense that our final units would be in pounds per square foot. Good, good. So, okay. We note, first of all, that the weight of the density of water is 62 pounds per cubic foot. So for the first question, when they say find the hydrostatic pressure on the bottom of the aquarium, what we do is we take the density of the water, 62 pounds per cubic foot, and we multiply that by 3 feet. So the bottom of the aquarium is 3 feet down. This is going to give us 187 pounds per square foot. That's the pressure acting on the bottom of the tank. So it's like a square foot on the bottom of the tank. Think of a 187.5 pound person sitting on the bottom of the tank. Can the glass withstand that? You know. How many have seen hydrostatic pressure maybe in another class? It might be a little advanced, but I know work you've seen in another class, but okay. Well, now next what we want to do, part B of the question said, find the hydrostatic force on the bottom of the aquarium. Okay, so we have the hydrostatic pressure on the bottom of the aquarium. That's 187.5 pounds per square foot. Now we have to find the hydrostatic force. Well, the way hydrostatic force is defined is, it is pressure times area. Pressure times area. I mean, what ultimately is the force going to have to be in? What units would the force need to be in for this problem? I find units very helpful.
Newtons?
What? Go ahead.
It's not newtons, is it?
Not newtons, not for this problem, because our unit of force is in
Pounds.
pounds. That's right. So force is in pounds. So force is going to equal the hydrostatic pressure times the area over which the hydrostatic pressure acts. So you take your 187 pounds. Hold on, I think I need a 0.5 here, right? Yeah, 187.5 pounds per square foot times 10 square feet, because the area of the bottom of the tank, well, the tank is 5 feet long, 2 feet wide, so the bottom of the tank is 10 square feet. That's going to get us 1,875 pounds. Okay, so that's the force acting on the entire bottom of the tank. Okay. Please let me know if you have any questions. The way I think of this, so you see the pressure is spread out over the area of the bottom of the tank, and yeah, well, that's fine. That's fine. Are there any questions? I mean, the way I like to think of this, sort of what helps me with this hydrostatic force. Let me go to the whiteboard to show you here to give you an intuitive feel for it. I think it's worth it. So this hydrostatic force is equal to pressure times area. So let's say that I want to be careful here how I phrase it. Okay, so maybe like a person, let's say, case one, you have a person that weighs 180 pounds per, I want to be square foot. In other words, I want to be a little bit careful how I phrase it, but let me just write it here. One moment here. Let's make this easier. Let's make this a little easier. Hold on. Okay, 200 pounds per square foot. Okay. And okay, let me just think here for a moment. Okay, let's do the 10 square feet. So this is going to be 2,000 pounds. Okay. Okay, and then second case, I'll just show you what I'm doing here. Okay, so I'm doing two hydrostatic force computations where the force is the same. Okay, so let's say that, I want to just phrase it the right way. Let's say that you have this is probably, all right, you have a person, well, I want to be careful here. Maybe a person standing on 1 square foot, and that person weighs 200 pounds. Okay, maybe a square foot, like in other words, per square foot, the person is 200 pounds. Spread across 10 square feet, it's 2,000 pounds. And then you have maybe let me see here. Well, not many people weigh 1,000 pounds per square foot, okay? But maybe like a polar bear or something, okay? Polar bear, 1,000 pounds per square foot, spread over 2 square feet, you get 2,000 pounds of force. So do you see that? Do you see that both the human and the polar bear, that the force exerted is 2,000 pounds? Does that make sense? Maybe this isn't a great example. I'll tell you what. Let's just don't worry about this example. Sometimes I think of intuitive examples. If I can come up with something a little more intuitive, I will. Let me just go back to the example here, okay? Let me just go back to the example. So far we've done A and B. Now we want to find part C, the hydrostatic force on one end of the aquarium. Okay, so we have part A, and we have part B, okay? And now we're looking at the one end of the aquarium, part C. So what I've done is I've drawn a picture of this aquarium. This aquarium, okay, is 5 feet wide. Well, hold on. Let me make sure. No, it's 5 feet long, 2 feet wide, and 3 feet deep. Now, we want to find the hydrostatic force on one end of the aquarium. And what I'm going to do here is I'm going to use a Riemann sum to do it. Okay, I'm going to use a Riemann sum to do it. Let me give you a moment to copy the picture down. The way we have the x-axis here is just like the problem where you pump water out of the tank. Well, I want to be a little careful. No. Yeah, that's right. So the x stands for how far down from the top of the tank you are. In this case, x is going to be between 3 and 0. Okay, so this is how you measure your x-axis. And with these problems, the x-axis is, they let it be the vertical axis. Okay, let me give you a moment to copy the problem down, or copy the picture down, and then we'll go into detail here. We're trying to find the hydrostatic force on one end of the aquarium. Okay, now we're going to need a Riemann sum to find this hydrostatic force. Like for part B, when we found the hydrostatic force for the bottom of the aquarium, okay, for the bottom of the aquarium, we didn't need to use, here's the bottom of the aquarium. We didn't need to use a Riemann sum. Okay, why is that? Why for part B, when we found the hydrostatic force on the bottom of the aquarium, all we needed to do was take the density of water and multiply that by the area of the bottom. Why was a Riemann sum not involved? What can you tell me about the bottom of the aquarium? For the bottom of the aquarium, what's true about the entire bottom of the aquarium?
It's filled with water.
It is down how far from the top?
2 feet, 3 feet from the top.
3 feet from the top. That's a constant. It doesn't matter. It doesn't matter where you are on the bottom of the aquarium. Every piece, every part of that bottom is 3 feet from the top. But this is not true. This is not true for the side of the aquarium. For the side of the aquarium here, and I'm picking the left side. You have like different layers. So like let's say that I have this layer here. Okay, this layer here. And I call that, that'll be one layer. And let me pick another layer here. Maybe a layer near, a layer a little higher. And I'll call this layer 1. And I'll call the other layer 2. Which layer 1, hold on. Which layer 1 or layer 2, is going to have, and again, once again, this is the side of the aquarium. Water is pushing against that side of the aquarium, right? It's pushing against it, right? How many have seen a container break? A container break because of water pushing against the side of a container. Okay, Samuel's seen that, Nathan's seen that. Okay, but I mean, this is just, if the material's not strong enough, the water's going to break out that side, like a dam. A dam, when a dam's constructed, that dam has to be strong enough to withhold the hydrostatic force acting on the wall of the dam. Okay, well, this left side here, this left side of the aquarium, you have different levels, and I'm showing level 1 and level 2. Which level is going to have a greater hydrostatic force acting on it? Which level of that wall on the left, level 1 or level 2, is the force going to be greater? That's right, level 2. And why level 2? Why does level 2 have a greater hydrostatic force acting on it?
Closer to the bottom.
Closer to the bottom. And that means that that's right, Maria. And when we find the hydrostatic force, or the hydrostatic force for that left end of the aquarium, it doesn't work like finding the hydrostatic force for the bottom of the aquarium. We have to use a Riemann sum to find the hydrostatic force for the left end of the aquarium. So what I need to do is I need to consider, okay, well, for the ith layer, let me do it this way, right? For the ith layer, ith level of the left side, if that level's xi feet down from the top, so the hydrostatic pressure would be 62.5 xi pounds over 1 square foot. The hydrostatic force, of course, it's still defined as pressure times area, but now what would the area be for the ith strip on the left? Well, the area would be 2 feet times delta x feet. Area is base times height. The width is 2 feet, right? So that's the width of that strip. Well, I'm really looking at this strip here, right? But the width of this strip here, okay, is 2 feet, because this here, I know it kind of, I should use the little line thing. This is 2 feet. So 2 feet times delta x gives you the area of that strip. And so the force, hydrostatic force on the ith strip is equal to 125 xi times delta x pounds. Now to get the total hydrostatic force, you add up all the hydrostatic forces for each ith strip of the left side of the tank, and you'll get and then of course, if you make the strip smaller and smaller and smaller, the Riemann sum will be more accurate. Okay, and you get this integral. Okay, are there any questions on that? Marcus? Yep.
So when you're multiplying the area, you did 2 feet for, I guess, like the width, right?
That's
If
correct.
you would like, well, that would be like the width for left or right, right?
That's
If you were to
correct.
do like the width of like, or I guess if you were to do like the front or back, would you use like 5 as the width instead?
You would. You
Oh, okay.
absolutely would.
All right,
Yep.
thank you.
Okay, you're welcome. Are there any other good questions before we move to the next page? Okay. So now we compute this integral, and we'll get 562.5 pounds. That will be the hydrostatic force acting against that end of the aquarium. I'd like to do one more problem before I set you off to work. So don't worry, a break is coming. Do not worry. Are there any questions at all? How many think this is pretty cool? Pretty interesting, pretty interesting. To have to see. Okay, Jacob's liking it. And hold on here, people are, Marcus, Tal, Sean, excellent, excellent. You're getting to see how calculus can be applied for engineering problems. Okay, so let's do one more example. Now this example in your homework, you're going to have a problem like this. Okay, and I wanted to do this one with you so that you would be comfortable doing this kind of problem. Let me give you a moment to copy the example down. Samuel, yes.
Would you mind going back, Professor, please?
Sure, sure. We'll go back here. This is the page. Okay. All right.
Thank you.
You're welcome. And everybody's good? Okay. All right. Okay, so yet another example, and I'll give you a moment to copy down the picture. Okay, so in this problem, a vertical plate is submerged in water, and the plate has this shape below. So this is the shape here. What do we call that shape, by the way, class? Do you remember from your middle school days?
Trapezoid.
That's a trapezoid. That's right. That's right, Maria. That's right, Jacob. And what we're doing is we're submerging this plate in water, and we want to find the hydrostatic force against one side of the plate. So we're dipping the plate into water here, and the water's going to put pressure on that plate. Now, notice that the plate, are we dipping the entire plate in the water?
No.
No. Here's the water level here. So basically, the only hydrostatic force acting on the plate occurs in this portion here, portion of the plate below the water. Now, the distance, of course, based on the picture, the distance well, how far down is the plate dipped into the water? How far down?
One meter.
1 meter. Here it is, right here, 1 meter. Okay, so that's what's relevant. But keep in mind how tall is the trapezoid based on the picture. How tall is the trapezoid? 2 meters. That's right. That's right, Nathan. All right, and so we're going to proceed now. This problem is well. Let's just work it out. But I think you already know that for this problem, we need to consider this plate below the water and break that plate up into strips, right? Just like the last problem, the part C of the last problem, the left-hand side of the aquarium, we broke that left-hand side up into strips. And each strip, we computed the hydrostatic force on the ith strip. We're going to do the same thing here. But the challenge here is that we need to find an expression for the area of this ith strip. That's where a little bit of the challenge is. So let me go to the next. Yes, question, Nathan?
Are we trying to find the hydrostatic force on the bottom or the sides?
Well, this plate, think of it like we're dipping the plate. It's the hydrostatic force. This is just like a thin plate. Pretend like it's thin. You're not worried about the side of the plate. You're worried about the front of the plate. This red part here that I'm highlighting.
Okay, I'm just a little confused because it says vertical plate. So I don't know if that means the sidewalls or...
Well, a vertical plate, just think of it as a plate. It's just a plate that they're putting in vertically in the water. That's what they mean. So they're not dipping the plate in the water at an angle. They're dipping it like directly vertically.
Okay.
Okay. All right. Good. So it's like the aquarium, the left end of the aquarium. That was vertical, right? Same thing here. Okay, so it's being submerged in this tank of water, and the water in the tank is pushing against the plate. We have to find the area of this ith strip. So here's what we need to do. So what we do is, first of all, the axis that I use, the x-axis, the x equals sorry, x equals 0 starts right at the water level. Okay, so this here is the water level, right? This is the water level right here. X equals 0 starts there, and then it goes down. Okay, so that's your x-axis. Now, what we have to do is we have to say, well, okay, the trapezoid was 4 meters across. Okay, 4 meters across. And let me just see here. One moment, class. One moment. Let me just see here. Yeah, because remember in the picture, the bottom of the trapezoid was 2 meters. So that means, you know, this here is 2 meters. And then if I break the trapezoid up into a rectangle and two right triangles, right? Each right triangle is going to have a base of 1 meter. So what we're going to do is we say, okay, well, this ith strip of the trapezoid is down a distance of xi meters below the water line. Okay, again, this here is your water line. And we want to find the area of that ith strip. So the area, of course, it's going to be base times height, but and you know, this is not like drawn completely to scale, but the full area, the full base here, the full base is this base right here. That's the full base. So yes, it includes the 2 meters, but it also includes this A, and then there's another A there. So in other words, the base for the ith layer of water is equal to 2 plus 2 times A. The question is, what is A equal to? Well, here's where we bring in similarity of right triangles again. You have here a big, right triangle that has base 1 and height 2. And then inscribed in it, you have a smaller triangle here, a smaller triangle, and I'm trying to draw it the best I can, that has base A and height 1 minus xi. Okay, because if this distance here is xi, then this distance here has to be the height, which is the height of that triangle. It has to be 1 minus xi, because xi and 1 minus xi add up to 1. And so therefore, by similar triangles, A divided by 1 minus xi here is equal to 1/2 there on the bigger triangle. The sides are in proportion. And therefore, A can be shown to be 1 minus xi divided by 2. Please let me know if you have any questions. Okay. Well, now the width of the ith strip is going to be that 2 meters plus 2 times A. And A is 1 minus xi over 2. So 2 meters plus 2 times 1 minus xi over 2 meters, that's going to get you 3 minus xi meters. Okay, 3 minus xi meters. This is your function. This is your function, you know, f of xi, that tells you the width of the ith strip xi meters down. Okay, that's what that is. If we didn't want to have the, well, yeah, that's fine. So now we find the area of the ith strip. That's going to be the width of the ith strip times the height of the ith strip. And that's just going to be 3 minus xi times delta x square meters. Once we have the area of the ith strip, okay, we're in good, well, we're moving in the right direction. But keep in mind, this problem doesn't deal with feet and pounds. It deals with meters. It deals with meters. And force then is going to be, when we have meters, what eventually is force going to be in? What units? Newtons.
Kilograms.
That's right, newtons. Newton, the force will be in newtons. Now what we have to do next, since force equals pressure times area, we need to find the pressure. So because we're dealing with a problem with metric units, we got to bring in gravity. So the pressure, okay, on the ith strip of that wall in that trapezoid is equal to the density times the acceleration due to gravity times the distance that the ith strip is from the water line. So therefore, the pressure for the on the ith strip, the hydrostatic pressure, is 1,000 kilograms per cubic meter times the acceleration of gravity, which is 9.8 meters per second squared, times the distance of xi meters. Again, I bring the units in because it helps me feel comfortable. When I, cancel the units out, like here, meters, that meters simplifies with well, you got a meters squared here. That simplifies with meters cubed to give you meters. And so you get a meters in the denominator. You also have times second squared in the denominator. And then you have kilograms on the top. And so this is going to be 9,800 xi pascals. Okay, that's a unit of pressure. How many have heard of pascals as a unit of pressure? All right, Michelle's heard of it, Sean and Jacob. All right, good. Okay, and so I know kilograms divided by meters times second squared is a pascal. And so how many find it helpful to bring the units, to kind of have those units in there? Okay, Jacob's liking that. And Samuel, Okay, good, good. It helps me, and I hope it helps you. Okay, well now that we have the pressure, now we're ready to compute the hydrostatic force on the ice strip. So I take the pressure on the ice strip, and notice it's a function of x sub I, the distance that ice strip is from the top of the tank, or top of the water line, sorry. It's going to equal the pressure times the area of the ice strip. And again, if you if you look at your units here, if you look at the units, meters here simplifies with meters squared there, giving you meters on top. And you end up with units that are kilograms times meters times seconds squared. And that is a Newton. That's your unit of force. How many knew that kilograms times meters times seconds squared? How many knew that this was defined as a Newton? Okay, Samuel knows that, and Jacob knows that. Good, good. So this is going to be 9,800 times 3 minus xi times xi times delta x newtons. That's the hydrostatic force on the ice strip. But we want the hydrostatic force on the entire, on the part of that plate that's submerged below the water. So what's the next step? What are we going to do with all these force expressions? What do we do with them, Samuel?
Integrate them.
Okay, and before we integrate, we have to create a
Riemann sum.
Riemann sum. We're going to add up all these forces. Okay, good, good. Now, in terms of the limits, just before I get there, in terms of the picture here, what would your limits be on your integral? What are your limits?
2.
Well, let's see here. Hold on. Hold that thought. Hold that thought. So here is the portion of the plate below water. Xi is the distance. It would be from 0 to 1. 0 to 1. This layer here at the very bottom, how far down is that from the water line?
Oh, it's 1 meter.
1 meter. That's right. Okay. This layer in the middle. This layer in the middle, how far down is it from the water line?
Half a meter.
About half a meter, right. The layer at the top, how far is it down from the water line?
0.
0 meters. Hence, your limits will be from 0 to 1. Good, good. Okay, well, now we take the Riemann sum. Absolutely amazing and beautiful, I'm telling you. There it is, and we come up with our integral. And if you work it out, you're going to get, in terms of scientific notation, 1.14 times 10 to the 4th newtons. That's what you're going to get. Now, there are other applications that you'll see in your homework as well, but those other applications that should have, most of them at least, like a help video or a master it, something to help you. How many use the help aids provided in the homework? from time to time. Wow, quick, all right, wow, okay, everybody's raising their hands. Okay, well, I'm glad to hear that. Very glad to hear that. They're there to help you. Good, good. And generally, my philosophy is try to do the problem without the help aid. But then if you need the help aid, you know, use the help aid. There are other areas too. There are other important applications. For instance, center of mass, the mass of a lamina, the balance point of a lamina is an important application. But I think for our second exam, I may cover that application and have it on the third exam, but I won't have it on the second exam. Okay. Because I think you have enough right now to keep you occupied. Are there any questions? Leping, yes.
Professor, can you go back one page?
Go back one page, okay. Here we go.
Yeah, for the pressure on S strip PI, why you multiply XI?
Because Xi is the distance that the ith layer of water is from the top of the water line. The pressure is dependent on, now remember, we're dealing in metric units here. So the problem we did previously, we computed the pressure a little differently, right? But with metric units, you take the density of your water, multiply it by acceleration due to gravity, and then multiply that by the distance that that layer of water is from the water line. All three of these elements play a role in computing the pressure. You can see they're all important. And incidentally, you know, we're dealing with the pressure of or the density of water, but you could have some other fluid like oil or something, you know, and you know, the concept would be the same. The pressure is dependent on the density of the fluid that you're working with. It's dependent on gravity, okay, and it's dependent on the distance that the ith layer is from the water line. Does that, Leping, you're okay? Okay, good, good, good. Getting an intuitive feel here. Okay, are there any other questions? Yes, yes. Leping?
Oh, sorry, it's accident. No.
Oh, okay, no problem. Marcus?
Yeah, I think you went over it already, but how did you get the limits from 0 to 1?
The limits, because the x sub I is defined as the distance from the water line. Here's the water line, right? Because this is full of water, right? Well, that distance xi, I mean the water is acting on this portion of the plate, right? So from here to here, distance goes from 0 to 1 because there's the distance from 0 to 1. That's how we get it. What's the distance for the bottom layer of water, Marcus? The bottom layer of water. What distance is that from the water line? How far down is the bottom layer of water?
Like from the
From
trapezoid or the
from this is the water line right here.
Uh-huh.
This is the water line.
That to the bottom, right? Of the
Right.
trapezoid?
How far is that?
1.
Right. So the bottom layer is 1 meter down.
Mm-hmm.
What about the top layer?
XI.
What's x equal to for the top layer?
1 minus XI.
Well, but let me ask you this. For the middle layer, how many meters down is the middle layer? Give me a number. Estimate.
Let's say like 0.5.
0.5 meters. Okay. Top layer, right at the top of the water line. How far down is that layer?
0.5.
At the top? At the very top?
Oh yeah. How far is that down from what? What did you say?
How far down is the top from the top?
Oh,
Let's put it
0.
that way.
Yeah.
0. Hence 1 to 0.
Mm-hmm. Okay.
You see how that works?
Yeah, more or less.
X sub I in the Riemann sum is the distance that the layer is from the water line. Well, any layer in the portion of the tank underwater will be between 0 and 1 meters from the top. That's why your limits are from 0 to 1. Very good question. You allowed me to re-explain that, which is excellent. Excellent. Okay, Marcus, you're feeling a little more comfortable?
Yeah, thank you.
Okay, you're welcome. Are there any other questions? Okay, I'll stop the recording.